focus is now on Möbius transformations under transformations of the complex plane. Previously, we had considered translation, that's Z becoming Z plus Z mapped to Z plus A. We've considered rotation and scaling, that's Z mapped to Z mapped to AZ. And then we considered inversion in the last video where Z is mapped to its inverse. That's inversion of the Z mapped to 1 over Z. So finally, we are here with Möbius transformations. Under transformations of the complex plane, we still have other videos after now. I mean, several, in fact. So let's go. So transformation of the complex plane with focus on Möbius transformations. So Möbius transformation is a function of the form f of z equals az plus b all over cz plus d, where a, b, c, d are complex constants, and ad minus bc must not be equal to 0, because if that happens, um, do I know the reason for that even? I think it's going to make this function undefined or something. I'm not sure. But AD minus BC must not be 0 in short. So these transformations act on the extended complex plane. It also acts on infinity. So the key properties of the Möbius transformations are as follows. Number one, they are conformal in nature. I mean, Möbius transformation is conformal in nature. I mean, it's angle preserving except at the poles. Then circle line preservation. Circles map to circles, lines map to circles or lines. Then it is also an invertible transformation, and it maps extended complex plane to itself. So we're going to see some of these things as we move on. So there's some special points here. Number one, it is undefined at z equals minus d over c. That is, in that case, c is not, for c not equal to 0, by the way. So I mean, how do we arrive at that? We know already that that transformation, the Möbius transformation, is generally given as az plus b over c x cz plus d. Okay, f of z is az plus b all over cz plus d. So where is this undefined? So for this to be undefined, right, cz plus d has to be equal to 0. And if that is the case, that means cz is equal to minus d, and then z is minus d over c. So if z is minus d over c, then that whole transformation is not defined. Of course, c must not be 0 at that point, actually. So what about the behavior at infinity? As z approaches infinity, yeah, that's another very crucial thing to consider. As z approaches infinity, what happens? Okay, so we have that f of z equals az plus b all over cz plus d. So what happens if we take the limit of f of z as z approaches infinity? So we have az plus b all over cz plus d. Now, if you remember under the calculus playlist, I talked about infinity. Like, I think 1 or 2 videos were dedicated to limits and continuity, maybe one or so. So in this case, normally the first thing you do when you have a limit problem is to substitute directly. So if you substitute infinity for z directly, you're going to get infinity clearly. But then if that is, but that's not conclusive. We can't conclude that the expression is going to be infinite just because z is approaching infinity. So we can look for other means. So the other means here is you can divide through by z. That's the highest power of z in this case. So we have limits of f of z as z approaches infinity. Okay, and that, so you can then divide through by z. So a over z, az divided by z, b divided by z, cz over z plus d over z, right? So we then have limit as limit of f of z. Uh, okay, I think I have a representation problem here. So it should be limit as it tends to infinity. So coming here, it should just be, this is not necessary again. So that means limit as z tends to infinity of, so this cancels. So we have a plus b over z all over c plus d over z. So as z approaches infinity now. So at this point, we can then substitute infinity. So we have a plus b over infinity C plus D over infinity. And the argument here is this, um, generally speaking, if you divide, let's say Z divided by zero, that is undefined, right? If that is the case, if you cross multiply, we have Z times 1 equals 0 times infinity. That means Z is equal to 0 infinity. So what does that mean? If you divide through by infinity, Z over infinity is equal to 0 infinity over infinity. Infinity cancels out. So Z over infinity is actually 0. In essence, anything divided by 0 is undefined, and anything divided by infinity is 0, basically. So with that argument, we can then go ahead and talk about what this expression is going to be. So now we are saying that limit of f of z as z tends to infinity now is the same thing as a plus b over infinity is 0, then d over infinity is also 0. So that means we have a over c. So we say that as z approaches infinity, f of z approaches a over c. So that's what we have in this case. See, these are special points now. This is undefined as z equals minus d over c. I've shown that. And behavior at infinity, for c not equal to 0, as z approaches infinity, the expression is a over c. Then if c is 0, of course, that's clear. If c is 0, we just have az plus b over d. So for c being 0, right? Um, again, it's the same expression. We have f of z equals az plus b over cz plus d. So, of course, easily at c equals 0, we just have f of z equals az plus b all over 0 times z plus d. So this is simply 0. So f of z is just az plus b all over d, if you like. And then we can tidy that up if you have very finicky like me. So a over dz plus b over d. That's what we have in the case where c is equal to 0. So those are some special points to note for Möbius transformation. Now we move on to decomposition of Möbius transformations. Every Möbius transformation can be decomposed into a translation. Say z can be so z can become z plus a. Then scaling and rotation, z can become kz, and then inversion, z can become 1 over z. So Möbius transformation is like the summation of everything we have seen under transformation in the complex plane. So every Möbius transformation can be decomposed into a translation, a scaling or rotation, and an inversion as a matter of fact. So, and then we talk about fixed points. So for fixed point, right, the key thing about fixed point is that a function is equal to its variable. That is f of x is equal to x. That's the idea of a fixed point, right? So, um, so just like the Godhead, right? God, the Father is equal to the Son, something like that. The Son is a function of the Father, right? But then the function f of father is equal to father, right? Or f of son is equal to son. So f of z equals z. So for fixed point now we need to solve f of z equals z, and then that means we have az plus b over cz plus d equals z, and then we try to solve this way. So this gives a quadratic. This quadratic gives at most two fixed points, right? I think I want to do that. I feel like I want to do that since I've been taking care of other things so far. Okay, so here, so let to find the fixed points, of a Möbius transformation. Okay, so of course we know a Möbius transformation is f of z equals az plus b all over cz plus d, right? So it's important to note that at a fixed point, f of z equals z. So what that tells us is that az plus b all over cz plus d is just equal to z, like that. So if you say that over 1 and cross multiply, so you have az plus b equals z into cz plus D, so that we have AZ plus B equals CZ squared plus DZ. So we can collect like terms. 0 is equal to CZ squared plus DZ minus AZ, right? Bringing this minus B. So we can tidy things up. We have 0 equals CZ squared plus D minus AZ minus B. Yeah, so we have that. So in essence, we have CZ squared plus D minus AZ minus B equals 0. So this is the expression we have. Well, you want to take it further and look for the actual, whatever, actual expressions, right? So we know in this case, um, for for ax squared plus bx plus c equals 0, right? We know that x can be given as minus b plus or minus square root of b squared minus 4ac all over 2a. That's the idea, or that's quadratic formula right there. So what do we have? So in this case now we can say that all the values are mixed up. So I want to carefully sort them out. So z is equal to minus b. Our b here would be this. So I don't want to write b because we also have b still. So our b here, pqr. Maybe I should do pqr. I think pqr makes sense here. So to avoid repetition to avoid confusion, right? So I can say that from 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 p, yeah, from px squared plus qx plus r equals 0, yeah? I think this is better. So x can be given as minus q, minus q plus or minus square root of q squared minus 4pr all over 2p, okay? So in this case now, from this expression, our p from here, now, P can be said to be C, P is C, then Q here is D minus A. That's D minus A. That is Q. Then our R there is minus B. So R is minus B. Yeah, I think that's about it. Then we can then put everything together. So, so Z now can be said to be equal to minus Q, that is minus D minus A, plus or minus square root of D minus A squared minus 4P, that's 4C, R is B, all over 2P, that's 2C now. So Z is equal to, this minus can change things over. So we have A minus D plus, or A minus D plus or minus square root of D minus A squared minus and minus plus, so that's 4bc all over 2c, like that. Yeah, we can still put this like this. Yeah, so this is what this looks like. So we have a minus z plus, a minus z minus. So these are the two fixed points we have in this situation. So that's the idea of fixed points. So but this is where this stops. So cz squared plus d minus az minus b equals 0. This quadratic gives at most two fixed points. And then we go for example 1. So consider f of z equals z minus 1 over z plus 1. What are the special values? At when z is 0, we have minus 1. When f is 1, when z is 1, so we have 0. When f is undefined, we have 1 because, we can do divide through by z and we have 1 over 1. So f at infinity is 1. So evaluate at 0, evaluate at 1 in this case, and evaluate at infinity. Then it is undefined at minus 1. When z is minus 1, this expression is undefined. As z plus 1 equals 0. So that means z is minus 1. So as z equals minus 1, the expression is undefined. So, and then we can talk about unit circle mapping. So if you consider f of z equals z minus I over z plus I, if absolute value of z is 1, then we say that we say z bar is 1 over z. This implies the transformation maps the unit circle to the real axis. So the transformation maps the unit circle to the real axis. That's what we see for this now. Okay. So if the absolute of z is actually equal to 1, that's unit circle mapping. Then for fixed points now, of course, we have 2z plus 3 over z plus 1 equals z. Then do all the rearrangements. You have 2z plus 3 equals z squared plus z. And then you have z squared minus, that's z squared, z minus 2z, that's minus z, then minus 3 if you transfer everything to the other side. And then using quadratic formula, z is 1 plus or minus square root of 13 all over 2, like that. And then we can work this out. We can do some plotting here. So here, you define Mobius with Z, A, B, C, D, and you return AZ plus B over CZ plus D, which is the definition. Then you can create a grid here. Then you can choose your A, B, C, D, whatever you want that to be. That's here we have chosen 1 minus 1, 1, 1. And then we then have W is Mobius with factors Z, A, B, C, D. And then you do the plot, and then we see the plots under there as we see it now. So this is the original plane we have, you know, and then from -2 to -2 on both sides. Then we also have transformed, we have the transformed plane here, after the transformation has been done. So we have the transformed plane. Then we have the unit circle. This is the unit circle, the circle with, I think, radius 1. That's the unit circle right there. So then we have the mapped curve, which is just a straight line. So that takes us to classification of Möbius transformations. How do we classify Möbius transformations? So based on fixed points, we can classify it based on rotation. So it can be elliptic, where it has rotation-like behavior. It can be parabolic, where we have one fixed point. Then it can be hyperbolic, where we have stretching along like this, and it can be loxodromic, where we have spiral behavior. Okay, for a Möbius transformation. Then we go on to talk about matrix representation. Actually, we can go very deep into Möbius transformation as on its own like that, but we just want to touch it briefly like a kind of intro. So for the matrix representation of Möbius, so each Möbius transformation corresponds to A, B, C, D. Composition of transformations corresponds to, so each Möbius transformation corresponds to this, and composition of transformations corresponds to matrix multiplication. So that's what we have there. And you remember the other time we saw the fact that AD minus BC must not be equal to 0. I think that's the determinant of this matrix we see here. Now you see this AD minus BC must not be 0. So you can relate it now with this matrix we have down here. Because if AD minus BC is 0, that means that the determinant of this matrix is not is equals, if AD minus BC is 0, that means the determinant of this matrix is 0, and then the matrix will not have an inverse. Okay. In summary, we have the general form of a Möbius transformation, which is f of z equals az plus b over cz plus d. So the key features, number one, it has conformal mapping, then it has circle line preservation, and then at most two fixed points. Then it is built from translation, scaling and rotation and inversion. So if you like, you can see Möbius transformation as the all in all of all kinds of transformations you can ever get in transformations that take place under in the complex plane, that is. So that's the deal with that. So now let's go ahead. As usual, we have our practice problems. So here, compute the image of the point z equals 2 plus I under f of z equals z minus 1, 2 plus 1. I think I'm going to, this is one of the problems I'm going to solve, right? Yeah, I'm going to solve 1 and 20 in this case, the first and the last. Yeah. So here you have 1 to 6, then you have 7 to 12, then you have 13 to the end, or maybe we can show 13 to the end, maybe 13 to 19 for then everything now to the end, 15 to the end. So now this one is saying verify that Okay, yeah, I'm solving question 1 and 20. First, question 1 says compute the image of the point z equals 2 plus I under f of z equals z minus 1 over z plus 1. And then question 20 says verify that the composition of two Möbius transformations is again a Möbius transformation. Show that f of g of z has the same form, basically. So we are going to show that all of this. So I'm going to answering questions 1 and 20, like I said. So let's start with the first question here. So, problem one. So want to compute the image of z equals 2 plus I under f of z equals z minus 1 all over z plus 1. Okay, so to compute that, right, what do we do? First of all, you know, um we have, okay, I can just say given f of z equals z minus 1 all over z plus 1. Given that, right, then f of 2 plus I, f of 2 plus I is equal to 2 plus I minus 1 all over 2 plus I plus 1. So that we then have, that's 2 plus I minus 1 over 2 plus I plus 1. So this is 2 minus 1, that's 1 plus I. 2 plus 1, that's 3 plus I. So with that in place, we can then rationalize. So I can just say rationalizing. So f of 2 plus I would have to be, we multiply by we multiply numerator and denominator by the conjugate of 3 plus I, which will be 3 minus I. So we have 1 plus I all over 3 plus I multiplied by 3 minus I all over 3 minus I. So the deal is that 3 minus I over 3 minus I is 1. And when you multiply anything by 1, nothing changes technically. All right. So this is now 1 plus I into 3 minus I up there. And then this is 3 plus I into 3 minus I down here. And the at the denominator level, right? That's difference of two squares to make things fast. So 1 times 3 is 3. 1 times minus I is minus I. I times 3 is 3I. Then I times minus 1 is minus I squared, right? So 1 times 3, 3. 1 times minus I, minus I. I times 3, that's 3I. I times minus I, that's minus I squared, all over difference of two squares, and that's 3 squared minus I squared, like that. So so we go on to say that f of 2 plus I is equal to, so we tidy things up now. 3 minus I plus 3I. This is minus already there. I squared is, and I squared is minus 1. I squared is minus 1 over 3 squared, that's 9. Then I squared again is another minus 1. So I'm taking it step by step so everything doesn't get mixed up. So f of 2 plus I is equal to 3 minus I plus 3I plus 1 all over 9 plus 1. So f of 2 plus I now is equal to 3 plus 1, that's 4. The minus I plus 3I, that's plus 2I. 9 plus 1 is 10. So 9 plus 1, I plus 1 is 10. So, of course, another thing I see here is that f of 2 plus I is the same thing as 2 into 2 plus I all over 2 times 5. So 2 cancels out, and then we have f of 2 plus I to be equal to 2 plus I all over 5. So we can split that up, and then we have 2 over 5 plus I 1 over 5. And that's what, so this is the image. So we can say, so the image, the image of z equals 2 plus I under f of z equals z minus 1 over z plus 1 is what we got there is 2 over 5 minus I 1 over 5. Or maybe I can just put it together, the same line. 2 over 5 minus I 1 over 5. Yeah, so this now. And that is question 1. Then we'll move on to question 20. That's problem 20. Yeah, which is a bit longer than the other question we just did. So let's look at question 20 again. So for question 20, now verify that composition of two Möbius transformation is again a Möbius transformation. So f of z is az plus b over cz plus d. G of z is ez plus f over gz plus h. Show that f of g of z has the same form. Okay, so let's go on that fairly long journey maybe. So we want to verify that the composition of two Möbius transformations is again a Möbius transformation. Okay, so we are given that f of z is equal to az plus b all over cz plus d, and g of z is equal to ez plus f all over gz plus h. So let's go for that. Let's move on with that now. So first we want to compute f of g of z. Okay. So first of all, like I like to do, right? f of z, or maybe let me not waste time with this now. We know already f of z is az plus b all over cz plus d. So we know that f of something, all right, is equal to a something plus b all over c something plus d. I like to put it that way. So normally this should be f of z equals az plus b all over cz plus d. So to avoid confusion, right? So now we want to look at f of g of z. So now instead of putting z there, we have g of z going in there. So f of g of z will now be a of g of z plus b all over c of g of z plus d. Okay, so I think that helps to make it clearer. Then with this out of the way, then we can say that f of g of z now is equal to, so now we know we are throwing in g of z into that place, and don't forget this is g of z right here. Okay, so we then have a into g of z, now that's ez plus f all over gz plus h, if that's correct. Yeah, so plus c all over d into ez plus f all over gz plus h, all of that plus e now plus gh, right? G, yeah, plus e, yeah, it's plus e here. So you can see it can be quite confusing. So this is abc, this is ab. Now, yeah, that can be quite confusing. A, B, C, D. So it's still the same thing we are following here. A, B, C, D. The only thing that has changed is that instead of Z now we have EZ plus H over GZ plus H, like that. Okay? So with that in place now, we now have to move carefully. So we know now that f of G of Z is now equal to, so we need to take LCM and do all of that. We need to simplify. So here now we know we have a into ez plus f all over gz plus h plus b over 1 up here if you like, all over c into ez plus f all over gz plus h plus d over 1 there. So we try to tidy things up carefully because it can be really confusing. So you have f of g of z equals, so the LCM up there is GZ plus H clearly. So GZ plus H goes here. So that's A into EZ plus F. But this now is B into GZ plus H, you know, all over, same thing, GZ plus H is the LCM down here. So that GZ plus H and GZ plus H, that's 1 times C. That's C into EZ plus F plus 1 goes into GZ plus H. So we have D into GZ plus H like this. So with this in place now, well, I think it's easy to just cross out the uh, denominators. This and this are the same. So we can cross them out. So we don't have to go through. Normally, I should say this over this, divided by this over this, and then we put it over GZ over H over. So it will now be this over GZ plus H times GZ plus H over this, and they will still cancel out. So, and then we still have the same. So with this cancelled out now, all we just need to do is just easily put them over themselves. So we have f of G of Z now equals at the top there we have a into EZ plus F plus B into GZ plus H all over C into EZ plus F, EZ plus F plus D into GZ plus H like this. And with all of that in place, yeah, I think we've done the most difficult part of the business, and then we can try to expand now. So expanding all of this, we have so f of G of Z equals AEZ plus AF plus BGZ plus BH. That's at the top there. Uh, all over down here we have C easy plus CF plus DGZ plus DH. Okay. And what is our goal? Um, so having done all of this now, so our goal is we want to show that this is also a Möbius transformation, that the composition of two Möbius transformation is another Möbius transformation. So now we have f of G of Z now equals, so now what can we collect? We can collect everything that has Z, we can put them together. So now we have AE, AE plus BG, that they both have Z, then plus the other side that doesn't have Z, AF plus BH all over down here, CEZ and DG, they have Z, right? So we have CE plus DG that have Z, all right, plus CF plus DH that doesn't have Z, okay? So with this now, it's looking like a Möbius transformation, another Möbius transformation already, because this can now be written as f of G of Z equals, so if you call this big A, so we have big AZ plus big B, then call this big C, big CZ now, plus big D. So, the original Möbius transformation has small a, small b, small c, small d. But now this one has big A, B, C, D, because each of those actually have a representation. So you can now say where big A is equal to AE plus BG, AE plus BG, big B is equal to AF plus BH, AF plus BH, then big C is CE plus DG. Big C is CE plus DG, and big D is CF plus DH. CF plus DH. And that's how it goes. So with that, now you can see this also looks like another Möbius strip. So we can then conclude by saying that the so we can say therefore the the composition has the same has the same form as a Möbius transformation. Has the same form as a Möbius transformation. Hence, we can say that Möbius transformations, Möbius transformations are closed, are closed under composition. Möbius transformations are closed under compositions. Yeah, that's a lengthy one, but we are done with that. So don't forget, try your hands on the questions again. Um, so you have questions 1 to 6 here. Then uh, don't worry if you see some questions you can't answer, just let me know. And I mean, I see this question 6 is talking about determining the pole. I've not talked about pole, but pole is simply if you equate 3z minus 4 equals 0. Whatever you get there is the pole, right? That makes this undefined. But we're still going to talk about all of those later, especially when we get to integration under complexity or something like that. So 1 to 6. 7 to 12, 7 to 12, then 13 to 9, 13 to 18, and then of course the rest. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos before others or seeing some videos exclusively as a member of the channel. You can also request for PDF copies of the notes I use in teaching, whatever topic the PDFs are available for. We can also hang out together virtually or physically if you're ever in the same geographical location to discuss whatever interests you on my channel. All right. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.